time and having a nice walk is definitely a kind of a trade-off. So for all economists in the room, I'm talking about an old hat. Well, basically because Pareto optimality is something well known in economics, well, I guess since several hundred years. So the idea is if you have several different objectives, say for example crop yield in a catchment and the minimum discharge in a catchment. The question is, well, how do we make these things comparable? You could either weight them by introducing some arbitrary weights or some educated guesses for the weights. You could put monetary values on it to make them comparable, or what I'm going to advertise here, use a Pareto optimality approach. That means looking at solutions that are not dominated by others. That means these are the solutions or kind of results of a model or kind of measurements where you cannot improve in one dimension, in one objective, without losing something the other. So if you look at that graph here, there are several model outcomes that have been aggregated to just two dimensions. Yield, sum of the yield, and minimum discharge at the catchment outlet, with different configurations, different crop rotations in different parts of the catchment. You get results for those. One point here is special, that's a red point, not because it's red, but because it's dominated. Well, you can have the same yield having a higher minimum discharge. That's beneficial. You can also have, vice versa, the same level of minimum discharge and a higher yield. So if these are the only two objectives you're interested in, and you believe in the model, why on earth would you pick that point? All other points are optimal, Pareto optimal. That means you cannot lose, cannot gain more minimum discharge without using some yield. This is what I'm interested in identifying. I'm not interested in picking a point on that. I think this is something to be done for decision makers, stakeholders, and so on. I'm just saying, well, this is kind of a functional trade-off, the best thing you can get. I'm not saying you're able to reach it. There might be policy constraints or other constraints where you cannot reach it, but kind of for a biophysical reality, kind of simplified by the model, this is the best you could get. Under some scenario assumptions about which crop rotations you use and stuff like that, the results look like that. A very simple example about the carbon pool in a medium-sized German catchment, plotted against, on the x-axis, the available arable land weighted by its suitability. Basically what this tells you, the different colors represent different assumptions about reforestation. Are we using deciduous forest, coniferous forest, mixed forest, and something in between? Basically it tells you, well, if you believe in the model, it would be best to first kind of reforest the worst soils. If you would reforest a very good soil first, well, this would definitely bring you somewhere here, below the Pareto frontier. So this would be suboptimal. You wouldn't go for that. The difference to scenarios basically is, well, you run more combinations. If you just have 4 or 5 scenarios, you have no clue if you are close to the Pareto frontier or if you're very far away from it. If you really test 10,000, 100,000 different combinations, then you might be able to estimate the Pareto, or you're able to estimate the Pareto frontier. And your scenarios might be close to it or might be far away from it. So therefore you cannot really, from my perspective, estimate functional trade-offs if you just look at scenarios. But still, of course, you cannot kind of simulate everything. Typically you have some boundary conditions, some scenario assumptions. For example, for reforestation, what are your boundary conditions? Which kind of climatic conditions do you assume? If it's about bioenergy crops, which kind of bioenergy crop systems do you kind of test and stuff like that? So, as I said, basically test all combinations if that's not possible. Then you have to rely on optimization techniques like genetic algorithm and stuff like that. This is another example from a medium-sized German catchment. We use a model, the soil water assessment tool, doesn't matter, catchment model. It takes input, for example, it takes in land use, management, like fertilization, and it takes in crop rotations. We tested that using different crop rotations, in total 39, some of those just focusing on food and fodder, others focusing on bioenergy production, based on a corn system or a two-culture system. You run the model, you get a result, in this case in 4-dimensional objective space, objective function, low flow at the catchment outlet, nitrate concentration at the outlet, the sum of food and fodder crops, the sum of bioenergy crops. And the optimization algorithm tries to optimize the crop rotation allocation and the different crop rotations in the catchment with respect to Pareto optimality of that four-dimensional objective function. And you get something like that. Not going into details. Don't look too close, it might give you a headache. Still get a headache if I look too close at it. You have, at the x-axis, you have yield for biogas crops, y-axis, yield for food and fodder crops. If the area is limited, there's an obvious trade-off. But you see some scatter. Well, because we have two more objectives. It's a four-dimensional space, so you have nitrate concentration, that is the size of the bubbles, and low flow, that is the color represented by the color of the dots. Basically, you see, well, there are more options, and if you look at different crop rotation systems, like a corn-based or a two-culture-based system, the trade-offs look a bit differently. And that's points I wanted to make. We don't have time for questions, I know. So